Hi, all. So circular motion is back, but now we're going to add in forces. So not just finding the velocity and the acceleration, you got to go that next step and then find the force after that. Okay, and you remember you'll always have an acceleration in circular motion, even if the speed is constant, because the direction changes. Okay, and acceleration is based on velocity, which is speed in a direction. Same exact slide from, thanks, Alexis. So same equations that we had before, same exact equations as we had before. Remember, acceleration always acts towards the center. Velocity acts tangent. Okay, and this is the instantaneous velocity. So it's not your average velocity, it's the velocity at that particular point. So at another point on your revolution, we're still going to see the acceleration go to the center, and this time the instantaneous velocity is tangent and going down. And that's how we're going to rotate around. So don't forget, we're going to have to use some circumference if we want to find some average velocity. So that would be the average velocity is the whole distance we traveled, and then the period or the time it took to go around one revolution. And do we have a new formula? So F equals ma. So your force is going to be times mass times acceleration. So same thing, m times RA. And you could also see it with the omega with the angular velocity mentioned. So you can work on this any way that makes you most comfortable. Just make sure you are identifying each unit first so that you do not get sidetracked. Make sure your units are correct, okay? So you're going to see we're going to have some different units sometimes. Sometimes we're going to talk about the universal gravitation force, and that is not your weight. That is your universal gravitation. So it is big G times the mass of one times the mass of the other divided by the distance squared. That distance squared is the center of the two objects. So you would get this distance measurement here. And some people call this R for radius, some people call it distance. So just remember it acts from the center to the center because our gravity force is also pulling you towards the center. Big G is this guy here. And here's your equations here. We've seen those before. And your mass of your Earth, that's going to come in a lot, is down here at the bottom. So remember, kilograms is good, meters is good, but you're going to see some kilometers. So anytime you see kilometers, you got to convert it to meters by multiplying by 1,000. So just go super slowly on any of those. A vehicle with a mass of 3,300 kilograms, so I told you right there it's a mass, is driving at a speed of 20 meters per second. That's our velocity around a level roadway with a curve. Okay, so that means we're just worrying about it in one direction, just coming right around the curve. The radius is 25 meters. Now you're just staying on the roadway, you're driving at the maximum space speed, but we have a constant speed. Okay, yeah, so we're going to keep that into the play. We're not putting really any gas on there. We're going around at a constant speed, so you're not going to be worrying about a true force applied here. We want to know the coefficient of friction between the tires and the roads. Okay, coefficient of friction, that is your mu. Okay, our weight is mass times acceleration. Most of these are 10, but just read carefully because with these high masses, it could really mess up your numbers. Your force of friction equals mu times the force of normal. That is your definition of it. Your force applied minus the force of friction is equal to mass times accelerating, because we still have acceleration even with constant speed because we're going in a circle and our direction is changing. However, we don't have that force applied. So then we can relate that to the force of friction is equal to mass times acceleration. And how is that going to help us out here? So do we know the mu? No, that is what we are trying to find. Do we know the force of normal? Well, we have the force of gravity and the force of normal. It's going around a level roadway. So our acceleration y is 0. So we know our force of normal is mass times gravity. Okay. We don't have a force applied. Okay. And we have a force of friction. Can we find that number yet? Not quite yet. Do we have our mass? 3,300. Do we have our acceleration? Yes. Here's how we find it. So you're finding acceleration, even if it says a constant speed, because we're going around on a circle. So for that one, you're going to take 20 squared divided by 25. That's going to give you your acceleration. And then, so you're going to plug your acceleration into that part. So now what do we have? The force of friction. And then you can plug that force of friction up into your top equation there to find your mu. So I know I'm not spelling it all the way out because I really want you to work on getting your algebra strong while we're leveling up here to the harder ones and for the test, because it's a lot of thick algebra and setting up the problems. So if you get stuck and you can't fit in those numbers and you can't get my answer, send me your work so that I can help you out there. And you can also, if you didn't want to use it in the multiple single equations, I find that if you struggle with math, you like to do it singularly, but I did give you the overall equation if you just had to substitute and solve because you can't follow the process there. And there's your answer, as long as I don't have any typos. How about this guy? A 1,500 kilogram satellite, that's our mass, orbits the Earth in a circular orbit as a height of 15,120 kilometers. I'm going to change that right now because I'm one of those people that forgets that I need to be in meters, and that's above the Earth's surface. So that is this distance right here, 15,120. 15,120,000. We also have to go center to center. So I need to add in the 638,000. Remember, that's kilometers. I need to change that into meters. Now, we're going to a satellite. So some of you are going, but wait, you said, well, in the large scheme of things, that little itty bitty distance from the edge of the satellite to the center of the satellite is negligible. We can ignore that distance because the other one is so great. So our distance or our radius that we're going to be using here is 15,000 or 15,120,000 plus 6,380,000. So that you're going to add those two numbers together. Okay, so the total radius is the radius of the Earth plus the height. Your G, 6.67 times 10 to negative 11. What is our equation that we are going to use? Okay, force of gravitation. Here we go. We have the G. Do we have the mass 1? Yep, 1,500. Do we have the mass 2? Where's the mass 2? 5.97 times 10 to the 24th. It's in kilograms. It's in kilograms, so we don't have to convert that. Radius is what we just found over on the other side. So there is our force of gravity. And then we go back and double check. Is that what the problem asks for? Some of the problems are going to stop here. They just want the force of gravity. But this one wants the speed. What equation do I have for speed? Okay. I have an equation that relates acceleration to speed. So I got to do what first? Find the acceleration. Okay. So now I can plug in my FG that I had, my mass that I had, and I'm going to find the acceleration. Now that I have the acceleration, I'm going to plug in my acceleration. I'm going to plug in my radius from before and solve for velocity squared. Remember when you are solving for that, velocity is going to end up being the square root of r times a. Could you just have this on your equation sheet? Yes, if you struggle with trying to solve for things with the squares, feel free to write this down. Okay, for our circular velocity is equal to square root of r times the acceleration. And here we go. And you can also go through and you could also use that formula there. I'm trying to show you that you have multiple different ways to go about things and practice your algebra skills. There's the answer to check it out on your own. And that's all for today.